Somewhere beyond the farthest galaxy ever seen, space may continue without end. No wall, no final shore, no last point where the universe simply stops. And yet, modern physics can still draw a boundary around infinity one that may shape light, black holes, and even the hidden architecture of reality itself. The deeper this question goes, the stranger it becomes. Perhaps the edge of the universe is not a place, but a horizon of information, or a surface capable of encoding everything within. If this kind of quiet cosmic mystery feels worth exploring, leave a like, subscribe for more science made for slow and thoughtful listening, and share the video with someone who enjoys looking beyond the visible sky. Thank you sincerely for spending part of your time here. What time is it where you are, and where are you listening from? Leave a comment and let the night sky connect distant places. Now, let the journey toward the edge of infinity begin. At first glance, the idea of an edge seems simple. A field ends at a fence, a table ends at its rim, a map ends at the border of the paper. The mind carries these ordinary experiences into the cosmos and asks where space itself stops, what lies beyond it, and whether the universe ends in darkness, emptiness, or some final wall. Yet the question becomes difficult almost immediately, because the universe is not an object placed inside a larger room. It is not known to sit within a surrounding emptiness that could be reached by travelling far enough. Space is part of the universe, and so is time. Any edge of the universe would therefore not be an edge inside space. It would be an edge of space itself, a limit beyond which distance, direction, and location might no longer have meaning. This is the first quiet shift in the problem. The familiar image of a border may be too small for what cosmology is trying to describe. Science distinguishes several very different ideas that are often gathered under the same word. One is a physical boundary, like the surface of a container. Another is an observational limit, beyond which information has not yet arrived. A third is a mathematical boundary, introduced to make an infinite geometry easier to study. These boundaries can look similar on a diagram, but they do not mean the same thing. A physical boundary would mark a genuine end to space. An observational boundary marks only the end of what can currently be seen. A mathematical boundary may represent infinite distance in a finite picture. Confusion begins when one kind is mistaken for another. The universe can possess horizons without possessing walls, and it can be mapped with edges without having an edge that any traveller could touch. The most immediate boundary in cosmology is the limit of observation. Light moves at a finite speed, and the universe has a finite age. The farther away a source lies, the longer its light takes to arrive. Telescopes, therefore, do not see distant objects as they are in a universal present. They see them as they were when their light began its journey. A nearby star appears only a few years in the past. A remote galaxy appears millions or billions of years in the past. Looking outward becomes a way of looking backward through cosmic history. Eventually the view approaches a time when the early universe becomes opaque, before light can travel freely through space. Even beyond that visible glow, there are regions whose signals have not had enough time to reach the present location. This creates the observable universe, a vast region centered on the observer and bounded by the greatest distance from which information can have arrived since the beginning of cosmic expansion. That boundary is often imagined as the outer edge of everything, but it is not. It is an edge of access, another galaxy, located far away. Has its own observable universe centered on itself. Much of its visible region overlaps with the region visible from Earth, but not all of it. In the same way, the horizon on a car motion does not mark the end of the sea. It marks the limit created by position, curvature, and line of sight. The cosmic horizon is more profound because it is shaped by the history of expanding space-time, yet its meaning is similar. It separates what can be observed from what remains causally hidden. Beyond it, space may continue for an immense distance, perhaps without limit. There may be more galaxies, more empty regions, and more patterns of matter that no telescope can ever reveal. The horizon says nothing by itself about whether the entire universe is finite or infinite. It only says that the visible portion is limited. This distinction becomes harder to hold because every observer is enclosed by a horizon. There is no external viewpoint from which the whole universe can be inspected at once. Cosmology builds its picture indirectly, using the large-scale distribution of galaxies, the ancient background radiation, the measured expansion of space, and the geometry implied by gravity. From these clues, it estimates the shape and behavior of regions far beyond direct reach. The result is not a photograph of the whole, it is a model tested against everything that can be observed and extended carefully beyond the observable boundary. Such models allow several possibilities. Space may be finite and closed, curving back on itself so that no edge exists. Space may be flat and infinite, extending endlessly in every direction. Space may be negatively curved and infinite, with a geometry unlike the flat spaces of everyday intuition. Each possibility changes the meaning of distance and parallel motion, but none requires a conventional wall. Even a finite universe need not have a border. The surface of Earth offers a simple lower-dimensional analogy. It has a finite area. Yet a traveller moving along the surface never reaches an edge. The path can continue until it returns to its starting point. The surface is finite but unbounded. A closed universe could behave in a related way across 3 dimensions of space. Travel in a sufficiently straight direction might eventually lead back toward the starting region, not because a force turns the path, but because space itself closes. The analogy is incomplete, since the surface of Earth curves through a larger surrounding space, while a closed universe does not need to be embedded in anything beyond itself. Its curvature can be intrinsic, meaning it belongs to the geometry of space alone. This reveals another source of confusion. Human vision tends to imagine curvature as bending into an outside dimension. General relativity does not require such an outside. Curvature can be measured from within through the behavior of distances, angles, and paths. Parallel lines may converge. Triangles may contain angles whose total differs from the familiar flat result. Light may follow routes that appear bent because space-time is curved. None of this requires a cosmic exterior. The universe can possess a complete geometry without being placed inside a larger geometric container. An infinite universe presents a different challenge. If space extends forever, then no physical edge exists at any finite distance. No matter how far a path continues, more space remains ahead. Yet mathematics often represents such infinity with a boundary. This is not done to claim that a wall waits at the end. It is done because infinity is difficult to handle in ordinary coordinates. Distances grow without bound. Equations may become awkward, and the global structure of space-time can remain hidden. By transforming the coordinates, an infinite range can be compressed into a finite diagram. Points that are infinitely far away can then appear along a line or surface at the edge of the map. The boundary belongs to the representation, but it can still carry deep physical meaning. It may indicate where light rays originate or end, how signals travel, whether regions can influence one another, and how fields behave at extreme distance. In this sense, a mathematical edge can reveal features of the universe that remain invisible in an ordinary picture. The strange result is that a universe can have no reachable boundary, while still possessing a boundary in a precise mathematical description. That boundary can organize the entire causal structure of space-time. It can separate paths that escape forever from paths that fall inward. It can distinguish the infinite past from the infinite future. It can turn questions about unreachable distances into calculations performed on a finite page. The edge is not a place waiting beyond the last galaxy. It is a statement about how the universe fits together when all distances and all times are considered at once. This is why the original question cannot be answered with a simple yes or no. An infinite universe has no edge in the ordinary physical sense. There is no final shore where space stops and an observer looks outward into something else. But infinity can acquire boundaries through geometry, causality, and mathematical transformation. Some boundaries describe the limits of observation. Others describe the ultimate destinations of light. Still others may encode the behavior of an entire region of space-time. The idea of an edge therefore survives, but in a changed form. It becomes less like a wall and more like a rule, less like a location and more like a relationship. Before the deeper boundaries of cosmology can be understood, the visible horizon must first be separated from the universe as a whole. The cosmos may extend far beyond every observable limit, and the first edge encountered is not the end of space, but the end of information. The observable universe begins not at a wall, but at a delay. Every source of light is seen after a journey, and every journey through space takes time. A star a few light years away appears as it was a few years earlier. A galaxy millions of light years away appears in a much younger state. The deeper a telescope looks, the farther back it reaches into cosmic history. Distance and time become inseparable, until the view approaches an age when the universe itself is young, hot, and filled with a glowing plasma that light cannot yet cross freely. The boundary of observation is therefore not drawn around space like the surface of a sphere made from matter. It is drawn through time. It marks the farthest past from which signals have had the opportunity to arrive. Cosmologists call this limit the particle horizon. Information travels at a finite speed. The universe has existed for a finite time. No signal can cross more than the distance allowed by those two facts, especially while space itself is expanding beneath the signal. The observable universe is the region from which light or some other causal influence can, in principle, have reached the present location since the early stages of cosmic history. Its boundary is not the same for every observer. Each location carries its own sphere of observable space, centered on itself. A galaxy far beyond the Milky Way has a horizon of its own. Much of its observable region overlaps with the region seen from Earth, yet part of it extends into places that remain hidden from terrestrial instruments at the present moment. The universe does not choose Earth as a center. The appearance of centrality is created by observation. Every observer stands at the center of a personal horizon, because incoming light arrives from all directions. This can make the cosmos seem enclosed, but the enclosure belongs to the flow of information rather than to the structure of space. The most distant light directly visible today comes from the cosmic microwave background, a faint field of radiation released when the universe is about 380,000 years old. Before that time, matter exists mainly as a hot mixture of charged particles and radiation. Photons scatter repeatedly from free electrons and cannot travel far in a straight line. Space is filled with light, yet it is opaque, like a dense fog. As expansion continues, the universe cools. Electrons join atomic nuclei, neutral atoms form, and photons begin to move freely across great distances. That release creates a surface of last scattering, not a material shell fixed in one place, but the distant layer from which the oldest freely travelling light now reaches Earth. It appears in every direction, because the early universe surrounds every later observer in time. Beyond that glowing surface, ordinary light cannot reveal earlier conditions directly. Other messengers may reach farther into the past. Neutrinos, particles that interact only weakly with matter, may carry information from an even younger universe, though they are difficult to detect. Gravitational waves may preserve traces of still earlier events. Even so, every messenger faces a horizon set by causality. A region whose influence has not had enough time to arrive remains outside the accessible past. The particle horizon is often described with a distance, but that distance requires care. The universe expands while light travels. A photon that begins its journey from a young galaxy crosses space that stretches during the voyage. The galaxy can now be much farther away than the simple product of light speed and travel time would suggest. For this reason, the present radius of the observable universe is not merely equal to the age of the cosmos expressed in light years. In the standard cosmological model, it is roughly 46 billion light years. This does not mean the light has travelled for 46 billion years. It means that the region which emitted the oldest observable signals is now about that far away when distance is measured according to the present cosmic expansion. Light always moves locally at the same speed, yet the distance between widely separated regions can increase as space expands. Very distant galaxies may now recede from Earth at an effective rate greater than the speed of light without violating relativity, because no object is racing through its local surroundings faster than light. The space between distant objects is growing. This expansion also creates another horizon, distinct from the particle horizon. The particle horizon concerns the visible past which regions have already been able to send information. The cosmic event horizon concerns the reachable future, which events will ever be able to influence a given observer, even if the universe lasts indefinitely. If accelerated expansion continues, light emitted today from sufficiently distant regions will never arrive. The gap grows too rapidly for the signal to overcome. Some galaxies seen now have already crossed beyond that future boundary, in the sense that their newly emitted light will rust permanently inaccessible. The ancient light currently arriving is a final record from a region that is slipping out of causal contact. The night sky therefore contains images of places that may never again communicate with the Milky Way. This does not place those galaxies outside the universe. It places them outside a future relationship. Horizons divide space-time according to possible connections. They do not necessarily divide existence into an inside and an outside. A particle horizon can expand as more time passes and more ancient signals arrive. An event horizon can remain finite because accelerated expansion limits future communication. Their sizes depend on the history of cosmic expansion, which is governed by the contents of the universe and the behavior of dark energy. If the expansion history were different, the horizons would also be different. A universe dominated by matter alone would possess another causal structure. A universe that eventually stopped expanding and collapsed would rearrange the future limits again. The shape of a horizon is therefore a record of how space-time evolves. This makes the observable boundary scientifically useful. Its existence helps explain why some regions of the early universe present a puzzle. Widely separated parts of the cosmic microwave background have nearly the same temperature, even though, under a simple as expansion history, they appear too distant to have exchanged light or heat before that radiation is released. This is known as the horizon problem. Cosmic inflation offers a leading explanation. It proposes that an extremely early period of rapid expansion stretches a once connected region across an enormous scale. Areas that later appear causally separated may therefore share earlier contact and similar conditions. Inflation does not remove horizons, it changes their history. allowing the visible universe to emerge from a much smaller region that has time to become nearly uniform before rapid expansion. The idea also implies that the total universe may extend vastly beyond the observable portion. The visible cosmos could be a tiny patch within a much larger domain. Evidence does not reveal the full size directly. Measurements show that space is very close to geometrically flat across the observable region, but near flatness does not prove infinity. A sphere of immense size appears nearly flat across a small patch of its surface. In the same way, a finite universe much larger than the observable domain could look flat within every region currently accessible. It may also possess a complicated global topology, connecting space to itself in ways that leave no outer border. Searches for repeated patterns in the cosmic microwave background attempt to test some of these possibilities, but no confirmed signature has established a finite cosmic shape. The horizon remains a limit on certainty as well as sight. Beyond it, cosmology extends known laws with caution. The large-scale uniformity of the visible universe supports the assumption that remote regions resemble nearby ones, but the assumption cannot be checked without incoming information. Space may continue smoothly. It may curve on scales too large to measure. It may contain an unimaginable number of galaxies, or it may eventually wrap around through a geometry that never presents a wall. The observable horizon does not settle these possibilities. It simply defines the region where evidence can arrive. Its apparent surface moves through cosmic history as new light reaches the present. Yet accelerated expansion also carries much of the universe toward permanent silence. The first cosmic edge is therefore both real and deceptive. It is real because no observation can ignore the limits imposed by light, time, and expansion. It is deceptive because nothing is known to stand there. No barrier blocks passage. No final layer of matter seals the visible sphere. The horizon is made from the absence of signals that have not arrived, and perhaps never will. It surrounds every observer without enclosing the universe, creating a boundary that belongs not to space alone, but to the web of possible cause and effect. A universe can be finite without ending anywhere. This idea appears contradictory only because ordinary objects have surfaces, borders, or walls. A room has a volume because its walls contain it. An island has an area because the sea surrounds it. A sheet of paper has an edge because it occupies part of a larger space. Cosmology allows a different possibility. Space itself can possess a finite total size while remaining complete in every direction, with no point where travel must stop and no exterior region waiting beyond it. The simplest guide is the surface of a sphere. That surface has a limited area, yet a path drawn along it never reaches a boundary. A traveller moving steadily in one direction can eventually return to the starting point without turning around. The surface closes on itself. It is finite, but it is unbounded. A closed universe extends this idea into 3 dimensions of space, instead of a 2-dimensional surface curving back on itself. All 3 spatial dimensions participate in the closure. Every local region can look ordinary. Nearby distances can be measured, stars can be mapped, and light can travel without meeting a barrier. Yet on the largest scale, space may connect back to itself. A sufficiently long journey could, in principle, return to its origin from the opposite direction. No wall causes the return, the geometry alone does. This kind of universe is often associated with positive spatial curvature. Positive curvature changes the relationships that flat geometry treats as fixed. On a flat plane, parallel lines remain the same distance apart. On the surface of a sphere, paths that begin parallel can eventually meet. Lines of longitude provide a familiar example. Near the equator, they may appear parallel, yet they converge at the poles. A triangle drawn across a sphere can contain angles that add to more than the flat result. In a positively curved universe, similar departures would appear in three-dimensional space. Very large triangles traced by light could contain an angle sum greater than the ordinary value. The volume contained within a sphere of a given radius could differ from the flat expectation. Parallel beams of light might gradually converge even in the absence of matter along their paths. The curvature would belong to space itself. The sphere analogy can mislead if taken too literally. A globe curves through a surrounding room, but a closed universe does not need to bend into a higher external space. Its curvature can be intrinsic. Creatures living only on a spherical surface could discover that their world is curved by measuring distances and angles without looking from outside. In the same way, cosmologists can describe spatial curvature through measurements made entirely within the universe. General relativity treats geometry as a physical structure. Matter and energy influence that structure, and the structure guides motion. The question of what lies outside a closed universe may therefore have no physical meaning. Outside is a directional idea defined within space. If space includes every possible location, there is no additional place toward which outside can point. The absence of an exterior is not the same as an exterior made of nothing. Nothingness still suggests a region in which no objects exist. A closed universe offers no such region. The geometry simply ends no more than the surface of Earth ends beyond the last longitude. Every direction continues into more space. The total amount of space may be limited, but its continuity is complete. This distinction separates a finite universe from a bounded object. A bounded object has an edge that divides it from something else. A finite unbounded space has no dividing surface. Its finiteness appears only in global measurements, such as total volume or the possibility of returning to a starting point. Locally, there may be no sign of closure. If the curvature scale is enormous, a small observed region can look almost perfectly flat. The surface of Earth appears flat across a field because the planet is large compared with the field. In the same way, a closed universe much larger than the observable region could appear flat to every current measurement. The absence of detected curvature would not prove that space is infinite. It would only show that any curvature is weak across the region available for study. Modern observations indicate that the observable universe is very close to spatially flat. This places strong limits on positive curvature, but it does not eliminate all finite possibilities. A vast closed universe can hide its global shape beyond the horizon. Its curvature radius could be so large that the visible cosmos occupies only a small patch. Even stranger finite geometries may also exist. Space can be flat locally and still possess a finite volume if its topology connects distant regions. Topology concerns how a space is joined rather than how it curves at each point. A flat sheet can be imagined with opposite edges identified so that crossing one edge leads back through the other. The resulting arrangement can be finite without requiring positive curvature everywhere. In 3 dimensions, similar identifications can create a universe that repeats through connected directions. Such models do not place physical seams in space. Light could circle the universe along several paths and produce repeated images of the same galaxy or patterns in the ancient background radiation. Searches for such repetitions attempt to reveal whether cosmic space wraps around on scales not much larger than the observable universe. No confirmed pattern has established this, but the possibility shows that finiteness and curvature are related without being identical. A universe can be positively curved and finite, or locally flat and finite through topology. It can also be infinite while possessing local curvature caused by stars, galaxies, and clusters. The global form cannot be read from one nearby measurement. It must be inferred from patterns spread across the widest available distances. The expansion of the universe adds another layer. A closed universe is not necessarily static. Its total volume can grow as space expands, even while its topology remains closed. The surface of an inflating balloon provides a limited analogy. Points drawn on the surface move farther apart as the balloon grows, yet the surface remains finite and without an edge. The cosmic version does not require expansion into an external room. Distances within space increase because the metric, the rule that defines distance, changes over time. A closed universe can therefore become larger without acquiring territory from outside. Every region separates from every sufficiently distant region as the geometry evolves. Its total volume increases, but no boundary moves outward into anything. Earlier cosmological models often linked positive curvature with eventual collapse. A universe containing enough matter might expand, slow, reverse, and contract. Current understanding separates geometry from destiny more carefully. The future depends not only on curvature, but also on the forms of energy filling space, especially dark energy and its long-term behavior. A positively curved universe could continue expanding forever if accelerated expansion dominates. Finiteness does not guarantee a final collapse, just as infinity does not guarantee endless expansion. Shape and fate are connected through the equations of gravity, but they are not interchangeable. If space is closed, a journey around it would be complicated by expansion. The universe may grow faster than any traveller can complete the circuit. Cosmic horizons may prevent signals from crossing the full geometry. Even if the geometry is finite, a place can exist within the same closed space and still remain permanently unreachable. Thus, a finite universe need not be fully observable. Its total extent may be limited while causal access covers only a fraction of it. The distinction between spatial closure and observational horizons becomes essential. One describes how space joins to itself. The other describes which events can exchange information. A closed cosmos can have no physical edge, and yet contain horizons that behave like boundaries of knowledge. The deeper lesson is that size does not determine whether an edge exists. A space can be infinite and unbounded, or finite and unbounded. What matters is not merely how much space there is, but how that space is connected. The instinct that every finite thing must end somewhere comes from objects embedded within larger surroundings. The universe may not belong to that category. If it is closed, there is no final location where geometry breaks, no last galaxy beside a wall, and no empty exterior beyond the wall. There is only more space ahead, gradually bending through a structure that may eventually return every sufficiently long path toward where it began. The cosmos could therefore possess a total volume, a global shape, and even a complete circuit without ever presenting an edge. Its finiteness would be hidden not behind a boundary, but within the quiet way every direction connects to every other. A flat universe seems, at first, like the simplest possible cosmos. Its geometry follows the familiar rules learned from ordinary space. Parallel lines remain parallel. The angles of a large triangle add to the expected total. The circumference of a circle grows in direct proportion to its radius. There is no global bending toward closure, and no outward flaring of negative curvature. Yet if this flatness continues without interruption, the apparent simplicity opens into something the mind cannot fully picture. Space may extend without limit in every direction, with no final region, no returning path, and no outer surface. Every distance can be crossed only to reveal more distance beyond it. An infinite flat universe is not merely very large. It does not possess a larger scale at all. Any boundary placed around a region belongs to the observer or to the chosen coordinates, never to the universe itself. The observable cosmos then becomes a finite island of information inside an endless geometric expanse. Beyond the particle horizon, more space continues, perhaps with galaxies, voids, dark matter, radiation, and structures shaped by the same physical laws. The horizon limits knowledge, but it does not suggest a wall. It resembles a circle drawn on an endless plane. The circle encloses a measurable region, while the plane continues beyond every point on its circumference. Unlike the surface of a sphere, however, a flat plane does not curve back toward itself. A traveller moving along a perfectly straight path never returns to the starting point through geometry alone. The journey has no natural completion. Extending this idea from a two-dimensional plane to three-dimensional space produces the standard image of an infinite flat cosmos. Flatness allows Euclidean geometry to hold across large scales, while infinity removes any global edge. General relativity describes local space-time as shaped by matter and energy, so stars, galaxies, and black holes curve their surroundings. The universe can therefore be globally flat while containing countless regions of local curvature. Gravity produces the local distortions, but when these are averaged over enormous distances, the total spatial geometry may approach flatness. Measurements of the ancient cosmic background, galaxy clustering, and other large-scale patterns indicate that the observable universe is very close to this condition. The data do not prove exact flatness across all existence, because observations cover only one finite region. They show that any overall curvature is small within the accessible cosmos. If the universe is truly flat and has the simplest possible topology, then it is also infinite. But if its topology connects distant locations, flat space could still possess a finite volume. Geometry describes local relationships, while topology describes the global pattern of connection. A flat universe may resemble an endless expanse, or it may wrap through hidden identifications that create repeated routes. Even so, the possibility of genuine infinity carries consequences that reach beyond size. In an infinite universe, there is no preferred center. Every large region can be treated as one part of a space that extends equally in all directions. From any galaxy, the observer sees distant galaxies receding on average because space expands. This does not imply that the observer occupies the middle of an explosion. Expansion is not matter flying outward from one central point into empty surroundings. It is the growth of distance throughout space. On an infinite plane marked with a grid, every gap between sufficiently distant points can widen, while the grid remains infinite before and after the change. No outer territory is required. Infinity does not become larger in the ordinary sense, yet distances within it increase. An infinite universe can expand without expanding into anything and without gaining an edge. Every finite separation grows according to the cosmic scale factor, while the total extent remains without limit. There is no outermost galaxy leading the expansion, and no boundary advancing through a surrounding void. Each galaxy sees the broad pattern centered on itself because the expansion occurs everywhere. On sufficiently large scales, the universe appears similar from place to place and direction to direction. This principle allows cosmology to describe expansion with a single evolving scale, even when the total spatial volume may be infinite. The infinity involved is not directly observed. It is inferred by extending a measured near-flat geometry beyond the horizon. Such an extension is reasonable within standard models, but it remains an extrapolation. The hidden universe may continue with the same average properties, or conditions may vary on scales far larger than the observable domain. Inflationary cosmology often suggests a total region vastly greater than the visible portion, and some versions allow spatial extent so enormous that it behaves as effectively infinite. Other versions produce many separate domains with differing histories. No signal can reveal the complete arrangement if regions remain permanently beyond causal contact. Infinity may therefore be a physical truth that no finite observer can verify by direct survey. No journey can finish the measurement, because confirming that space never ends would require crossing an endless distance. Observations can constrain curvature and topology, but infinity itself always lies partly beyond experiment. Mathematics handles this more calmly than intuition. An infinite flat space is described without needing to imagine all of it at once. Coordinates assign positions, equations define fields, and symmetries reveal how the system behaves under shifts and rotations. Yet infinity introduces its own difficulties. Total quantities can diverge. An infinite universe filled with matter may contain an infinite amount of mass. If stars existed eternally in a static infinite space, every line of sight might eventually end on a stellar surface, making the night sky bright. The darkness of the sky helps reveal that the universe is neither infinitely old in a static state, nor filled with unchanging stars. Cosmic expansion, finite stellar lifetimes, and the finite age of observable light resolve that old puzzle. Infinity in space does not imply infinity in the visible past. A universe can be spatially endless while having a limited age since its hot early phase. Every present observer then occupies a finite causal region, even though space at that moment may continue forever. The beginning of expansion is not necessarily a point located somewhere in space, in a flat infinite model. The early hot state occurs everywhere. As the cosmic scale factor decreases toward the past, distances between all regions shrink, but the spatial extent can remain infinite at every moment. Infinity multiplied by a smaller scale remains infinity. The young universe is denser and hotter, not necessarily enclosed within a tiny external volume. The common image of all matter exploding from one location belongs to ordinary explosions, not to standard cosmic expansion. Every region emerges from an earlier, more compressed state, and no unique center can be identified. This means that even the phrase beyond the universe begins to lose meaning. In an infinite flat cosmos, any supposed beyond would have to lie past an endpoint that does not exist. Space already includes every direction and every reachable location. Adding an exterior would simply add more space and make it part of the universe being described. The edge cannot be approached because there is no distance at which it waits. No matter how far a signal travels, its path remains internal to the cosmos. The only limits it encounters are horizons created by time, expansion, gravity, or causality. These limits can be absolute for communication, but they do not terminate space. A galaxy may disappear forever beyond an event horizon, while continuing to exist within the larger geometry. The separation becomes permanent, yet neither side occupies an outside. They are regions of one universe whose future paths no longer meet. The endlessness of flat space is therefore less dramatic than a wall, and more unsettling than one. A wall would provide a final location and a clear distinction between here and beyond. Infinity denies both. It replaces the last place with an unending sequence of places, each locally ordinary and each followed by more. The universe may have no final galaxy, no farthest void, and no ultimate darkness at the end of distance. Its large-scale geometry may remain almost featureless in its flatness, while its extent surpasses every possible journey. The apparent simplicity of parallel lines conceals a cosmos that cannot be circled, completed, or viewed as a whole. If such a universe has an edge, that edge cannot be physical. It must arise from the limits of information, or from a mathematical transformation that brings infinity into a form the mind can study. The next step toward that transformation begins when flatness gives way to a stranger geometry, one in which parallel paths separate, and space grows more rapidly than ordinary intuition expects. Negative curvature begins where familiar geometry stops behaving quietly. In flat space, two straight paths that begin parallel remain separated by the same distance. On a sphere, paths that begin parallel eventually bend toward one another and meet. In negatively curved space, the opposite happens. Parallel paths drift apart, and the farther they continue, the faster their separation grows. The geometry opens outward. Circles contain more area than flat intuition predicts. Triangles contain less angular sum, and distances spread through a landscape that seems to create room faster than ordinary space allows. A simple image is a saddle, curved upward in one direction and downward in another, but that image captures only a small local patch. A complete negatively curved space cannot be represented without distortion inside ordinary flat surroundings. Its true form extends without limit, and every region resembles every other region. No central saddle point exists. The curvature is woven into the space itself. Mathematicians call the two-dimensional version hyperbolic geometry. Cosmology extends the same idea into 3 dimensions of space, where every direction participates in the negative curvature. Such a universe is often described as open. If its geometry is simple and extends uniformly, it is infinite. A traveller moving along a straight path never returns through global closure. There is no outer wall, yet the geometry differs fundamentally from an infinite flat universe. In flat space, the amount of room inside a sphere grows according to a familiar relation with its radius. In hyperbolic space, the enclosed volume grows much faster. Each step outward reveals more possible directions and more available space than the previous step suggests. The result is an infinity that feels not merely endless, but expansive at every scale. The idea can be seen through triangles. On a flat surface, the 3 angles of a triangle add to a fixed total. On a positively curved sphere, the total is greater. On a negatively curved surface, it is smaller. The larger the triangle becomes, the more strongly the curvature reveals itself. A tiny triangle may appear almost flat because every smooth geometry resembles flat space over a sufficiently small region. This is why daily experience offers little guidance. Rooms, roads, and planetary distances are too small to display the global shape of the cosmos. Cosmologists must use structures extending across enormous portions of the observable universe. Patterns in the cosmic microwave background act like ancient rulers. Their apparent sizes help reveal whether light paths converge, remain parallel, or diverge as they cross cosmic space. Present measurements show no strong departure from flatness. But negative curvature remains important because it exposes how infinity can acquire a boundary in mathematics. Hyperbolic space contains an unusual abundance of room. Consider a set of equal shapes arranged without gaps. On a flat floor, only certain regular polygons fit perfectly around a point. Equilateral triangles, squares, and regular hexagons can tile the plane in simple repeating patterns. A sphere is more restrictive because positive curvature closes the available area. Hyperbolic space behaves in the opposite way. Its outward opening allows many arrangements that flat space cannot contain. Regular polygons with numerous sides can meet around a point without crowding. Countless forms of regular tessellation become possible. Every tile can have the same true size even when a drawing makes tiles near the apparent edge look smaller. That shrinking is not a property of the hyperbolic world. It is a consequence of compressing an infinite geometry into a finite image. The most familiar model is the Poincaré disk, a circular map in which the entire infinite hyperbolic plane fits inside a finite rim. Straight paths in the hyperbolic geometry appear as arcs that meet the circumference at right angles, while paths through the center appear as ordinary straight lines. Shapes preserve their local angles but shrink toward the rim. A tile near the boundary looks tiny on the page, yet within the geometry it is identical to a tile at the center. An inhabitant moving toward the rim would never become smaller and would never arrive there. Each step would reveal more tiles ahead. The apparent boundary remains infinitely far away. No location inside the disk is privileged. A transformation can move any chosen point to the center while preserving the internal geometry. The rim always retreats to infinite distance around the new center. The circle is not a physical shell. It is infinity represented as a boundary. That boundary gathers every possible direction of escape into a finite surface. A path can approach a particular point on the rim forever, and that point records the direction in which the path travels toward infinity. Different routes may end at different boundary points, even though none reaches a final physical location. The boundary organizes the asymptotic behavior of the geometry, meaning the way paths and fields behave at indefinitely great distances. In ordinary language, it describes what the space approaches without claiming that any traveller arrives there. Negative curvature also changes the relation between nearby paths. Two light rays or free trajectories can separate rapidly, even if they begin with only a slight difference in direction. This does not require a force pushing them apart. The geometry itself creates the divergence. In cosmology, an open universe can expand as well, and cosmic expansion adds another form of separation on top of spatial curvature. These ideas must not be confused. Curvature describes the geometry of a spatial slice, while expansion describes how distances change with time. A negatively curved universe can expand quickly, slowly, or according to a more complicated history depending on its matter and energy. Dark energy can dominate its future just as it can in a flat or positively curved universe. Geometry does not determine fate by itself. The term anti-de Sitter space introduces a more specific form of negatively curved space-time. It is not simply any open cosmological universe. It possesses a constant negative curvature in space-time and is shaped by a negative cosmological constant. In its simplest form, it does not describe the observed universe, whose expansion appears associated with a positive dark energy density. Yet anti-de Sitter space has become one of the most important settings because its structure is unusually orderly. It has a well-defined boundary at infinity, and signals can interact with that boundary in ways that allow the interior to be studied with remarkable precision. The geometry acts like a controlled laboratory for questions involving gravity, quantum fields, black holes, and the possibility that a higher dimensional world can be described by information on a lower dimensional surface. The route toward that idea begins with the Poincaré disk. A single disk represents two dimensions of negatively curved space at one instant. Stacking such disks through time creates a space-time diagram resembling a cylinder. The interior represents the higher dimensional bulk, while the cylindrical surface represents the boundary at spatial infinity carried through time. The surface has one fewer spatial dimension than the interior. Although it appears finite in the compactified picture, it corresponds to locations infinitely far from every point in the bulk. The strange feature is that this boundary is not merely decorative. Conditions placed there can influence which solutions are allowed inside. Waves can move outward, reflect according to chosen boundary rules, and return. Fields in the interior can be related to patterns defined at infinity. Gravity shapes the bulk. Yet the boundary provides a stage on which parts of the bulk physics may be encoded. None of this turns the rim into a wall of matter. It remains a mathematical limit, but the limit behaves with enough consistency and structure that physics can be formulated upon it. This is where the meaning of an edge begins to shift again. In an infinite flat universe, infinity can feel directionless and remote, a place that is never reached and barely enters ordinary calculations. In negatively curved space, infinity is organized into a surface. Every outward direction approaches some point on that surface. The boundary preserves information about angles, paths, and fields even while physical distances diverge without bound. It becomes possible to ask not only what lies near infinity, but what mathematical data must be specified there to determine the interior. The answer can be rich enough to suggest that the boundary and the bulk are not independent descriptions. They may be two expressions of the same underlying physics. That possibility belongs to later sections, but its foundation is geometric. Hyperbolic space shows that an infinite universe can appear to possess an edge when represented in the right coordinates. The edge stays unreachable, yet it remains precise. It contains no final galaxies and no border guards of nature. It is a map of endless directions, a record of how the geometry opens, and a quiet surface on which infinity leaves its trace. Before such a surface can carry the information of an entire universe, infinity must first be compressed without destroying the relationships that make the universe what it is. Infinity becomes easier to study when it is brought closer without being made smaller in any physical sense. The task is not to shorten the universe, remove distant regions, or pretend that endless distance has a final point. It is to change the way distance is represented. A road stretching forever can be drawn on a finite page if each new portion is given less room than the one before it. The road still contains an unlimited sequence of places, but the intervals between their marks shrink toward the edge of the drawing. No traveller on the road notices this compression. Only the map changes. In physics and geometry, a related process is called compactification. An infinite space or space-time is transformed so that its entire extent fits within a finite coordinate range. Infinity appears along a boundary of the new map, while every finite physical location remains inside it. This is not an arbitrary artistic trick. A useful compactification preserves the relationships needed to understand motion, causality, and geometry. It does not preserve every ordinary distance. If it did, infinity could not fit into a finite picture. Instead, it protects selected structures while allowing scale to change from place to place. The most important version for spacetime is conformal compactification. A conformal transformation preserves angles where curves intersect, even though it may stretch one region and compress another. Tiny shapes retain their local form while their displayed sizes change. A square may become smaller near the boundary, but its corners remain right angles. Two paths meeting at a certain angle continue to meet at that angle after the transformation. This property is especially valuable in relativity, because the paths of light define the causal structure of space-time. If the transformation is chosen carefully, light rays keep the same characteristic diagonal direction on the map. The distances and durations shown by the coordinates are altered, but the distinction between possible and impossible influence remains visible. Events that can exchange signals stay causally connected. Events that cannot exchange signals remain separated. The map compresses infinity without erasing the order of cause and effect. A simple mathematical example begins with an endless line. Each point on the line can be assigned a new coordinate that approaches a fixed limit as the original coordinate grows without bound. Moving farther along the physical line produces smaller and smaller movement on the compactified map. 1,000,000 additional units may occupy a visible interval near the centre, while an unimaginably larger distance occupies a thinner interval near the edge. The boundary itself represents no finite point on the original line. It stands for the direction in which positions continue forever. Reaching it would require passing through every finite distance, which cannot be completed by any ordinary journey. Yet the boundary can be written into equations. It becomes possible to ask what a field approaches there, whether a light ray ends there, and how the geometry behaves in the infinite limit. When time is compactified together with space, the entire history of a space-time can sometimes be displayed inside a finite diagram. The infinite past, infinite future, and infinite spatial directions acquire distinct places along the diagram's edges. A world line, the path traced by an object through space-time, then reveals not only where the object moves but where its history begins and ends in the compactified structure. Massive objects follow time-like paths and remain inside the cones set by light. Light follows null paths along the cones themselves. Hypothetical faster-than-light motion would cross outside them. Because conformal maps preserve these angular relationships, a finite diagram can display the global causal design of an infinite cosmos. Regions that look impossibly remote in ordinary coordinates can be compared directly. Horizons can be identified as lines beyond which signals fail to escape. Singularities can be separated from harmless coordinate failures. The destiny of light can be followed toward infinity as clearly as a river can be followed toward a coastline on a map, even though the coastline in this case may represent an unreachable limit rather than a physical shore. The need for such maps becomes clear near black holes. Some coordinate systems make the event horizon appear singular. Quantities become infinite there, suggesting that the geometry itself breaks. A different choice of coordinates reveals that the apparent failure belongs to the map. An observer falling through a sufficiently large, quiet horizon does not encounter an infinite wall at that location. The old coordinates have stretched the horizon into a false boundary. New coordinates can cross it smoothly and expose the true division between events that can still send signals outward and events whose future remains trapped. Compactification extends this lesson from deceptive infinities at finite locations to genuine infinity itself. It allows the edge of an infinite spacetime to appear in the same finite representation as stars, observers, horizons, and black holes. The transformation must be read carefully. Equal lengths on the page do not represent equal physical lengths. Equal steps near the boundary correspond to ever greater intervals in the original geometry. The boundary may look close to an interior point, but its true distance remains infinite. A light ray can reach certain parts of this boundary in the compactified diagram, because the diagram includes infinite time as well as infinite space. This does not mean a photon crosses an infinite spatial distance in a finite physical duration. It means the completed history of the ray is represented from a viewpoint that compresses the entire temporal extent. In some spacetimes, light reaches infinity as time also extends without limit. In others, the geometry allows signals to arrive at a conformal boundary in finite coordinate time, while the physical interpretation depends on the spacetime being studied. The map gathers these possibilities into a common visual language. Conformal compactification also reveals that infinity is not always one undifferentiated destination. There can be a future reached by massive objects that persist forever, a different future approached by escaping light, and spatial infinity representing directions that extend outward at a fixed time. Past infinity can likewise be divided according to the kinds of paths that emerge from it. These distinctions are hidden when infinity is treated merely as a very large number. They become clear when each class of endless path meets its own part of the boundary. The resulting structure acts like a skeleton of space-time. It shows how histories connect, where information enters, where it leaves, and which regions remain forever unable to communicate. This skeleton can remain stable even when the interior contains complicated matter and local curvature. Far from stars and galaxies, the geometry may approach a simpler form, and the boundary records that asymptotic simplicity. Physicists can then define incoming and outgoing states at infinity, compare them, and study how the contents of the universe transform one into the other. A particle scattering experiment, for example, can be imagined with particles beginning far apart in the distant past, interacting in a central region, and separating again into the distant future. Compactified coordinates place those remote beginnings and endings on finite boundaries, allowing the full process to be described as one connected pattern. The same method becomes more subtle in curved spacetimes, where gravity changes which infinities exist and how they are joined. A black hole removes some future paths from the boundary and directs them toward a singular interior. An expanding universe can create horizons that divide accessible infinity from regions that never communicate. A negatively curved anti-de Sitter spacetime gives its infinity a time-like boundary, one that persists through time and can remain in causal contact with the interior. Each geometry writes a different arrangement along the edge of its compactified map. The edge is therefore not added after the physics is solved. It helps define what kind of physics the spacetime permits. Boundary conditions determine whether waves escape, return, vanish, or reflect. They help select which solutions to the equations are physically meaningful. An infinite universe still has no material rim, but its behavior at infinity cannot always be ignored. The distant limit may control the interior as quietly as the shape of a musical instrument controls the notes that resonate within it. Compactification makes that influence visible without claiming that infinity has become a nearby place. It changes scale, not reality. It brings endless paths into a finite frame while preserving the angles that light and causality require. In doing so, it turns the vague phrase edge of infinity into a precise collection of boundaries, each associated with a different way of travelling through space and time. The universe remains unbounded, yet its global structure can now be held within a diagram, and the boundary that seemed impossible begins to acquire a language of its own. A Penrose diagram begins with an act of compression, but what it reveals is not merely a smaller picture of space-time. It reveals the order of infinity. An ordinary space-time diagram places time on one axis and space on another. Light rays move diagonally, while massive objects follow slower paths inside those directions. The trouble appears when the diagram tries to include an infinite universe. Spatial distances run without limit. Time may extend endlessly into the past or future. No page can contain the whole structure at a constant scale. Roger Penrose's solution is to change the scale while preserving the causal angles. Distant regions are squeezed closer together, and distant moments are compressed toward finite edges. The result places all of space-time inside a bounded shape, while light still travels diagonally. The picture does not preserve physical distance, but it preserves which events can influence which others. Its boundary is therefore more than decoration. Each part of the edge represents a different kind of infinity, and the arrangement of those parts tells the story of the space-time as a whole. In the simplest flat space-time, an observer can remain at one place forever. That world line rises through the diagram and approaches future time-like infinity, the destination of massive objects that survive without accelerating to the speed of light. Traced backward, the same world line approaches past time-like infinity. A ray of light behaves differently. It moves outward at the maximum causal speed and approaches future null infinity, a diagonal boundary associated with escaping radiation. Incoming light originates from past null infinity. A path extending outward at one moment approaches spatial infinity, which represents endless distance rather than duration. These infinities are not interchangeable. Matter cannot arrive at null infinity. Light cannot end at time-like infinity, and spatial infinity is not a future destination. The diagram assigns each endless behavior its own place, turning the single vague word infinity into a structured set of limits. The preservation of light cones makes this possible. At every event, a light cone separates reachable slower than light directions from those forbidden by causality. In a two-dimensional Penrose diagram, these cones appear as crossing diagonal lines. A massive object moves within the cone. Light travels along its edge, and no physical influence crosses outside. Because conformal compactification preserves these angles, the light cones retain their orientation even as enormous distances shrink near the diagram's boundaries. The visual scale changes, but the causal relationships survive. A short line near the edge may represent an immense span, yet its direction still distinguishes matter, light, and forbidden motion. This allows a Penrose diagram to display questions that ordinary coordinates often hide. Can a signal escape from a region? Can two observers exchange messages? Does a path end at infinity or at singularity? Does a horizon mark a true physical divide or only a failure of coordinates? The answers become visible through the way paths approach the boundaries. A black hole provides the clearest example. In familiar coordinates, the event horizon may appear as a place where time freezes and mathematical quantities become infinite. The Penrose diagram shows that the horizon is not the end of space-time. It is diagonal surface that light can cross inward but cannot cross outward. Once a world line passes through, every future directed path remains inside the black hole region. The singularity appears not as a distant point in space, but as a future boundary that lies ahead of anything that falls inward. This reveals that the singularity is unavoidable after the horizon is crossed. The horizon itself is defined globally. It separates events that can eventually send signals to future null infinity from events that cannot. Locating it requires knowledge of spacetime's entire future, not merely one moment. The diagram therefore displays a boundary whose meaning depends on infinity. Without future null infinity, the event horizon cannot be defined in the same way. In a collapsing star, the horizon can begin forming before the central singularity appears, because its identity is tied to which rays will fail to escape in the completed history. This is a quiet power of the Penrose picture. It presents the whole causal story at once, allowing local events to be understood through their relation to remote futures. The same method clarifies expanding universes. A cosmological horizon can divide events that will ever be visible from those that remain permanently beyond contact. With accelerated expansion, future infinity may become space-like, stretching across the diagram as a boundary approached by every sufficiently long-lived observer. Light rays may reach that future boundary without ever crossing from one isolated region into another. The geometry creates event horizons around observers, limiting the portion of space-time from which signals can arrive. A universe can then be spatially vast or infinite, while each observer inhabits a finite causal domain. Penrose diagrams make the distinction visible. The total space-time occupies the full compactified shape, while an individual observer's accessible region forms only part of it. Knowledge ends at an interior horizon, not at existence's outer boundary. Different cosmologies produce different diagrams because they possess different causal structures. A universe that begins with a hot early state may contain a past space-like boundary, associated with the Big Bang. This does not make the beginning an ordinary surface somewhere in space. It means that, within the classical model, past-directed world lines reach a limit after finite proper time. A universe that recollapses may end at another space-like boundary. An eternally expanding flat universe may instead open towards several kinds of future infinity. Anti-de Sitter spacetime has a time-like boundary, represented by vertical edges that remain present through time. Signals can reach this boundary and return, so conditions imposed there become essential to the behavior of the interior. Each diagram is a compressed signature of the universe it describes. A diamond, triangle, strip, or cylinder is not chosen for appearance. Its shape follows from which infinities exist and how light connects them. The diagrams can also join regions that intuition separates. The maximally extended description of an eternal black hole contains more than one exterior region, linked through a geometry that cannot be crossed from one exterior to the other by an ordinary traveller after the bridge forms. The diagram reveals horizons, interiors, singularities, and additional asymptotic regions in one coherent structure. Some regions arise only by extending an idealized solution beyond what a collapsing star creates. The diagram does not decide which extension nature realizes. It shows what the equations permit when carried to their full causal completion. This distinction protects the method from being mistaken for a literal photograph. Penrose diagrams simplify spatial dimensions, suppress local detail, and often assume symmetries that real astronomical systems only approximate. They do not show the size of a black hole, the density of a star, or the exact curvature at each point. They show the pathways available to information. In that role, they expose truths that detail can conceal. Their boundaries are especially powerful because physical theories often depend on what fields do there. Incoming radiation can be specified at past null infinity. Outgoing radiation can be measured at future null infinity. A gravitational disturbance in the interior changes the relation between those states. The infinite boundary becomes the place where a complicated history is summarized by what enters and what leaves. Stephen Hawking's analysis of quantum fields around black holes depends on this kind of comparison. Vacuum states defined in the distant past and distant future do not match when a horizon forms between them. The mismatch appears as particle creation, showing that emptiness changes across evolving curved spacetime. Infinity provides the clean regions where those states can be defined, while the interior geometry explains why they differ. The Penrose boundary participates in physics without becoming material. It offers a stable reference for describing processes that unfold through gravity and time. An infinite universe still has no reachable outer edge, but the completed paths of matter and light gather along precise mathematical limits. Past and future separate. Light-like and time-like destinies diverge. Horizons emerge as boundaries between possible and impossible communication. The diagram turns infinity into structure, and structure into physical insight. What first appears to be a frame around the universe becomes a map of every way a history can end. Along that frame, light approaches its final directions. Massive objects approach their distant futures, and the causal design of space-time becomes visible in a form small enough to hold on a page. A boundary at infinity becomes physically important when equations need to know what enters a space-time, what leaves it, and what conditions remain there after every finite region has been crossed. Fields do not exist only at isolated points. They spread, oscillate, carry energy, and respond to curvature. A field may represent light, matter, gravity, or a quantum possibility distributed across space. To predict its behavior, physics must specify more than the local equations. It must also state how the field behaves at the edges of the region being studied. In a laboratory, those edges may be the walls of a cavity, the surface of a conductor, or the ends of a vibrating string. In an unbounded universe, the relevant edge may lie at infinity. This is why mathematical boundaries can affect real predictions without becoming material surfaces. Consider a wave equation. The equation permits many possible patterns. Some waves move inward, some move outward, some grow without limit, and some remain stable. Boundary conditions select the patterns that belong to the physical situation. A field may be required to vanish at infinity, approach a constant value, carry only outgoing radiation, or contain a specified mixture of incoming and outgoing disturbances. Each choice changes the solution. The local law remains the same, but the global behavior differs. In flat space-time, physicists often assume that particles begin far apart in the distant past, interact in a limited region, and separate again in the distant future. The remote past and future provide clean places where the particles can be treated as nearly free. What happens between them is encoded in the relation between incoming and outgoing states. The boundary records what arrives and what departs. Gravity complicates this picture because space-time itself responds to energy. A massive body bends the paths of particles and light. While radiation can alter the geometry through which later radiation travels, even so, if the space-time becomes sufficiently flat at great distance, fields can still be defined near past and future infinity in a controlled way. The complicated central region is then compared with simpler asymptotic regions, where asymptotic means the behavior approached at extreme distance or extreme time. This comparison makes it possible to describe gravitational waves leaving an isolated system, particles scattering around a massive object, or quantum fields evolving near a black hole. A black hole changes the relation between the boundaries of past and future. Before the hole forms, incoming modes of a quantum field can be defined in a region that appears empty and nearly flat. After collapse, some paths escape toward future null infinity while others cross the horizon and never return. The field is divided by the causal structure. What counts as an empty state in the past no longer appears empty to observers studying the outgoing field in the future. The reason lies not in matter leaking from inside the horizon, but in the way positive and negative frequency components are mixed by the changing geometry. Frequency here is tied to how a field oscillates relative to a chosen notion of time. In curved and evolving space-time, different observers or different eras need not agree on the same division. A state containing no particles according to the distant past can contain particles according to the distant future. Hawking's calculation uses this mismatch. Quantum field modes are traced through the space-time of a collapsing object. Some approach the forming horizon, where their phases become enormously stretched when described from far away. Others reach future infinity. By comparing the field's initial vacuum state with the outgoing modes detected at great distance, the calculation produces a thermal spectrum. The black hole radiates with a temperature determined by its surface gravity, a measure related to how strongly the horizon influences nearby trajectories. The result does not require a physical membrane at infinity. It requires a clear definition of the field in regions where the geometry becomes simple enough for particle states to be identified. Infinity supplies those regions. The horizon supplies the separation that prevents all parts of the field from remaining accessible to one observer. Together they transform the meaning of vacuum. Popular descriptions often picture pairs of particles appearing beside the horizon, with one falling inward and the other escaping. That image can offer a rough intuition, but it is not the full calculation. The deeper account follows quantum modes across the entire causal geometry. The radiation is a global effect. It depends on how the past boundary, the collapsing matter, the horizon, and the future boundary fit together. A physical prediction may emerge from relationships extending from one infinity to another. The boundary does not merely frame the calculation. It provides the language in which the initial and final states can be compared. Black hole evaporation then gives boundaries an even more troubling role. If radiation carries energy away, the black hole slowly loses mass. In the simplest picture, it eventually disappears. Matter and quantum information that cross the horizon seem to be replaced by thermal radiation that reveals almost nothing about the original state. Ordinary quantum mechanics preserves information in the evolution of a closed system, so a complete loss would signal a deep conflict between gravity and quantum theory. The information paradox is therefore a dispute about global evolution. It asks whether data entering through one part of space-time can be recovered from what reaches another boundary. Future infinity becomes the place where the final radiation is collected in principle. The question is whether that boundary contains enough structure to reconstruct what fell into the whole. If it does, the radiation cannot be perfectly featureless. If it does not, quantum mechanics may need to change. This problem has driven the idea that surfaces and boundaries store more information than classical intuition expects. Black hole thermodynamics already points in that direction. The entropy of a black hole, which measures the number of microscopic states compatible with its visible properties, scales with the area of the horizon rather than with the volume hidden inside. A region that seems three-dimensional has a maximum information content controlled by a two-dimensional surface. The horizon is not the same as the boundary at infinity, yet the two are linked through the behavior of fields and radiation. Information passes across one and may later appear at the other. The geometry between them determines whether the accounting remains complete. Boundaries also influence classical fields around black holes. To calculate a stable configuration, the field may be required to remain regular at the horizon and behave in a chosen way at infinity. These two conditions can leave only certain solutions. Disturbances around a black hole produce characteristic ringing patterns, called quasi-normal modes. The waves fall inward at the horizon and travel outward at infinity, with no incoming radiation added from either side. Those boundary rules select a discrete set of complex frequencies. The resulting tones reveal the black hole's mass, rotation, and surrounding geometry. When merging black holes send gravitational waves across the universe, the fading ring-down observed far away carries this boundary-shaped signature. In anti-de Sitter space, the role of the outer boundary becomes stronger still. The boundary is time-like, meaning signals can reach it and return. Waves do not simply disappear forever into endless distance. Their behavior depends on what is imposed at the boundary. Reflecting conditions can trap radiation, allowing it to interact repeatedly with the interior. A black hole in this setting exchanges energy with surrounding fields under rules fixed at infinity. The boundary can act like the wall of an idealized cosmic chamber, although it remains infinitely far away in physical distance. Because the conditions there influence the bulk so directly, the boundary becomes a natural place to define an alternative description of the same physics. The path toward holography grows from this unusual control. An infinite edge can hold the data needed to determine gravitational events inside. The broader lesson is that a boundary need not be touched to matter. Physics is built from local laws joined to global conditions. The laws describe what can happen at each point, while the conditions decide which complete history is realized at infinity. Those conditions distinguish empty space from incoming radiation, stable fields from divergent ones, and escaping signals from trapped information. Around black holes, they help define horizons, radiation, ringing, evaporation, and the fate of quantum states. The edge remains absent as a wall, but present as a demand placed upon every solution. In this form, infinity is not beyond physics. It is one of the places where physics quietly decides what the universe is allowed to do. Anti-de Sitter space gives infinity a shape that behaves almost like a place. It remains infinitely far from every ordinary point, yet its boundary persists through time and can exchange signals with the interior. This makes it unlike the distant edges of flat space-time, where outgoing light may escape and never return. In anti-de Sitter geometry, the outer limit is time-like. A light ray can travel outward, reach the conformal boundary in the compactified description, and come back after boundary conditions redirect it. The boundary is not a shell of matter and not an end to the underlying geometry. It is the organized form taken by spatial infinity when negative curvature and time are combined. That organization turns an unreachable edge into one of the most important structures in modern theoretical physics. A simple picture begins with the Poincaré disk. The disk contains an entire infinite hyperbolic plane. Every tile has the same true size, even though tiles appear smaller near the rim. The shrinking belongs to the map, not to the geometry. Moving toward the rim never brings a traveller closer to a physical wall. Each step reveals more space ahead, and the remaining distance stays unbounded. The circumference records possible directions toward infinity. When time is added, a sequence of such disks can be stacked into a cylinder. Each circular slice represents space at one moment, while the cylinder's surface carries the boundary through time. The interior has two spatial dimensions in this simplified picture, while the boundary has only one. Both share a time dimension. The pattern generalizes. A higher dimensional anti-de Sitter bulk possesses a boundary with one fewer spatial dimension. This difference in dimensionality is the foundation of the holographic possibility. The term bulk refers to the full interior space-time where gravity acts. Stars, particles, black holes, and fields would inhabit this region if the model were treated as a physical universe. The boundary has no independent thickness in the compactified geometry, yet it can support fields of its own. These boundary fields are not simply shadows thrown outward by objects in the interior. They can form a complete mathematical theory with their own interactions, observables, and evolution. The remarkable claim is that the boundary theory and the bulk theory may describe the same physics in different languages. Before that claim can be understood, the boundary itself must be treated carefully. Anti-de Sitter space has constant negative curvature in space-time. Its natural length scale determines how strongly the geometry bends. Near any small region, the laws of local physics can still resemble those of ordinary relativity. Across large distances, however, the curvature changes the behavior of light and matter. The gravitational potential acts in a confining way. Objects and signals that move outward do not simply disperse forever as they might in flat space. Their trajectories are drawn back toward the interior, or they interact with the boundary conditions imposed at infinity. The space-time behaves in some respects like a perfectly reflecting chamber, with an infinitely distant wall compressed into a finite diagram. The chamber image is useful only if the wall is understood as mathematical. Nothing solid occupies the boundary. Instead, the equations require rules there because the boundary can influence future events inside. This causal contact gives the anti-de Sitter boundary unusual power. In many spacetimes, information sent outward becomes permanently inaccessible. In anti-de Sitter space, a disturbance can reach infinity and return within a finite interval of the natural global time coordinate. Without a boundary condition, evolution may not be uniquely determined. The field equations alone cannot say what happens when the disturbance encounters infinity. It might reflect, vanish, or return with a changed phase. Different choices produce different physical theories. A well-defined anti-de Sitter model therefore includes a rule for the boundary. The edge participates in the definition of the universe. This is not a weakness unique to exotic geometry. Ordinary physical systems also require boundary conditions. A string fixed at both ends vibrates differently from a string with free ends. Light in a mirrored cavity forms different patterns from light in open space. What makes anti-de Sitter space strange is that the relevant boundary lies at infinite physical distance while still remaining causally active. The universe behaves as though its most remote limit can answer back. Negative curvature also makes the relation between boundary scale and bulk depth precise. In the Poinsot representation, motion toward the boundary corresponds to examining shorter distance scales in the boundary theory. Motion deeper into the bulk corresponds to larger scales. A change in position along the extra-radial direction can therefore be interpreted as a change in the scale at which boundary physics is described. The bulk's additional dimension is connected to the organization of information by size or energy. This does not mean the radial direction is unreal. It means that one theory treats it as geometric distance, while the other treats it as a hierarchy of scales. The same structure can appear as space in one description and as pattern in another. Black holes make this relation even more revealing. An anti-de Sitter black hole occupies the bulk and possesses a horizon with entropy proportional to its area. On the boundary, the corresponding state can behave like an ordinary quantum system at a temperature. The gravitational object and the thermal field state are two views of one arrangement. Changes in the black hole can be translated into changes in the boundary theory. Radiation, collapse, equilibrium, and entropy become questions that can be studied without placing quantum mechanics directly inside a strongly curved gravitational interior. The boundary offers a language where gravity may be absent or easier to handle, while the bulk offers a language where geometry is central. The correspondence between them suggests that space-time itself may emerge from quantum relationships encoded on the edge. The anti-de Sitter boundary is conformal. Conformal symmetry preserves angles and ignores absolute scale. A conformal field theory behaves similarly across different magnifications, at least in the idealized form relevant to the correspondence. This symmetry matches the way the anti-de Sitter geometry treats changes in radial position. A transformation that shifts the bulk toward or away from the boundary can resemble a rescaling of the boundary coordinates. The geometry and the field theory possess compatible symmetries, making a detailed equivalence possible rather than a loose analogy. Every operation on one side has a counterpart on the other. A particle in the bulk corresponds not to one simple point on the boundary, but to a distributed pattern in boundary fields. A local event inside may be encoded non-locally across a broad boundary region. This spreading helps explain how a lower dimensional surface can contain information about a higher dimensional volume. The information is not stored like tiny pictures placed side by side. It is woven into correlations among quantum degrees of freedom. The deeper an event lies in the bulk, the more widely its boundary representation may be distributed. Recovering the interior requires understanding these patterns as a whole. This gives the word boundary a second meaning. It is the limit of the compactified geometry, but it's also a complete stage for an alternative universe. From the bulk viewpoint, the boundary lies infinitely far away. From the boundary viewpoint, there is no bulk direction at all. There is only a lower dimensional quantum theory evolving in its own space-time. Neither description is placed physically outside the other. They are proposed to be equivalent. The higher dimensional gravitational world and the lower dimensional non-gravitational world contain the same information, organized differently. The edge does not surround the universe like a container. It expresses the universe in another form. The observed cosmos is not known to be anti-de Sitter. Large-scale measurements instead indicate accelerated expansion, associated with the geometry closer to de Sitter space. This limits any direct claim that the real universe possesses the same kind of boundary. Anti-de Sitter space is valuable because it offers a controlled setting where quantum gravity can be studied with mathematical precision. Lessons learned there may extend beyond it, but that extension remains incomplete. The boundary of the actual universe could behave differently, and a fully established holographic description of an expanding de Sitter cosmos is still absent. Even so, anti-de Sitter space proves that an infinite edge can be more than a convenient line on a diagram. It can carry a complete physical description. It can determine how waves behave, encode black holes, organize scale, and replace a gravitational interior with a quantum theory one dimension lower. Infinity remains unreachable as distance, yet it becomes immediate as information. The edge of anti-de Sitter space is therefore neither a wall nor an illusion. It is a mathematical boundary with physical authority, a surface that does not end the universe, but may describe everything that happens within it. The holographic possibility begins with a disagreement between appearance and accounting. A region of space seems to contain information throughout its volume. Matter can occupy different positions, fields can vary from point to point, and gravity can shape the interior in countless ways. Ordinary intuition therefore expects the amount of information to grow with the size of the volume. Black hole physics suggests another rule. The entropy of a black hole grows with the area of its horizon, not with the volume behind it. Entropy measures how many microscopic arrangements can produce the same visible state. If gravity allows no object to contain more entropy than a black hole of the same size, then the maximum information inside any region may also be controlled by its boundary area. A three-dimensional volume may hold no more fundamental information than a two-dimensional surface can encode. This is the seed of the holographic principle. The name comes from the way a flat hologram stores the appearance of depth, but the physical idea is more exact and more radical. It does not claim that the universe is a visual projection or that familiar objects are unreal. It proposes that a theory defined on a lower dimensional boundary can contain everything needed to describe a higher dimensional region. The interior and the boundary would not be separate systems linked by a rough resemblance. They would be equivalent descriptions of the same underlying physics. One description may contain gravity and curved space-time. The other may contain quantum fields without gravity. Events that look local in the interior may appear as distributed patterns on the boundary. A black hole may appear as a thermal state. A direction through space may appear as a change in energy scale. Geometry itself may emerge from relationships among quantum degrees of freedom. The most precise realization of this idea is the correspondence between anti-de Sitter space and a conformal field theory. In its best understood examples, a gravitational theory in an anti-de Sitter bulk is mathematically equivalent to a quantum field theory living on the bulk's lower dimensional boundary. The correspondence does not merely match broad features. Quantities on one side can be translated into quantities on the other. A field in the bulk corresponds to an operator in the boundary theory. The value of that field near the boundary acts as a source that influences the boundary operator. The response of the boundary theory carries information about how the bulk field behaves. Different states in the quantum theory correspond to different geometries or distributions of matter in the interior. A black hole in the bulk corresponds to a hot state on the boundary. The formation and evaporation of such a black hole become forms of ordinary quantum evolution in the lower dimensional description. This is important because quantum evolution preserves information. If the boundary theory is complete and unitary, meaning probabilities remain consistent and information is not destroyed, then the bulk process it describes must also preserve information. The apparent loss caused by a black hole horizon cannot be fundamental. Information may be hidden in correlations too subtle for a simple thermal calculation to reveal, but the boundary description suggests that it remains present. Holography therefore offers one of the strongest clues that the black hole information paradox has a resolution within quantum mechanics, rather than through its abandonment. The exact mechanism remains difficult to express in ordinary spacetime language. The boundary theory may encode an interior object across many degrees of freedom at once. No single boundary location needs to correspond to one single bulk point. The mapping is often non-local. Information about a central region can be spread over a large part of the boundary, protected by patterns of quantum entanglement. Entanglement describes correlations that cannot be reduced to separate properties of individual parts. Two regions may share a joint quantum state even when neither region carries the complete description alone. In holographic models, the structure of entanglement appears closely tied to the structure of space. The amount of entanglement between parts of the boundary can correspond to the area of certain surfaces extending through the bulk. Changing the entanglement pattern changes the geometry associated with it. Reducing entanglement can cause parts of the bulk to separate. Increasing it can bind regions into a more connected spatial structure. Space may therefore be less fundamental than the network of quantum relationships from which it emerges. The smooth interior is not painted directly onto the boundary. It is reconstructed from correlations. This reconstruction resembles an error-correcting code. In such a code, information is distributed across many components so that the loss of a few components does not erase the message. A bulk event may be recoverable from several different boundary regions, even though none seems to contain a simple copy. This redundancy helps explain how the interior can appear local and stable, while its information is stored non-locally. It also offers a way to understand why data behind a horizon might remain encoded in the boundary theory. The information is not hidden at one inaccessible point. It is woven into the total quantum state. A boundary observer with complete control of the theory could, in principle, reconstruct parts of the bulk that ordinary local observers cannot reach. This does not provide an easy method for retrieving objects from a black hole. It reveals a deeper equivalence in the description of the state. The bulk retains its practical reality. Falling objects still cross horizons, curvature still affects motion, and local experiments still behave as though space-time is present. Holography changes what counts as fundamental, not what counts as experienced within the theory. The lower dimensional description may be more basic in one mathematical sense, but neither side is merely an illusion. They are like two coordinate systems that reveal different structures, except the transformation is far more profound. One side contains an extra dimension and gravity. The other replaces that geometry with quantum interactions. A difficult gravitational problem can sometimes become an easier field theory problem, while a difficult, strongly interacting field theory can sometimes become a simpler geometric problem. The correspondence gains power precisely because the two descriptions organize complexity differently. When one is strongly coupled and hard to calculate, the other may be weakly curved and easier to study. This has allowed holographic methods to illuminate not only black holes, but also strongly interacting quantum matter. Yet the method's greatest conceptual force remains its claim about space, information, and boundaries. An infinite anti-de Sitter universe possesses a conformal boundary at infinity. That boundary is one dimension lower than the bulk, but it can encode the bulk completely. Every particle, field, and gravitational disturbance corresponds to some boundary pattern. the word edge becomes almost misleading. The boundary does not sit beside the universe as its final surface. It is another full description of the universe. The interior does not end there in the way a room ends at a wall. Instead, the entire interior is translated there. Infinity becomes the location in the compactified mathematics, where the alternative theory lives. The apparent edge contains the whole. This success does not prove that the observed cosmos is literally a hologram of the same kind. The large-scale universe resembles a space-time with positive accelerated expansion, rather than anti-de Sitter space. Its future boundary has a different causal character, and no equally complete correspondence is known. Attempts to extend holography to cosmology continue, but the path is less controlled. A boundary may lie in the distant future rather than around space. The theory associated with it may not behave like the conformal field theories already understood. Observations do not currently reveal a direct holographic encoding of galaxies, stars, or human-scale objects on a cosmic surface. The principle remains a powerful framework grounded most firmly in special mathematical settings. Even there, however, it changes the meaning of what an edge can be. A boundary can be infinitely distant and still contain every fact about the interior. It can have fewer dimensions and still describe a world with more. It can preserve information that appears lost behind horizons. It can turn geometry into entanglement and depth into scale. The universe inside the boundary may be no less real, but its reality may be shared with another description that has no interior at all. The edge then ceases to be the place where existence stops. It becomes the place where existence is rewritten. The question returns in a quieter form. Does an infinite universe have an edge? The ordinary answer remains no. An infinite space does not end at a final wall, and no last galaxy marks the place where existence gives way to an exterior. Yet cosmology has uncovered boundaries too important to dismiss as mere tricks. The observable horizon limits which regions can have sent information. The event horizon limits which events will ever be able to do so. Conformal compactification gathers endless distances into finite diagrams. Penrose boundaries classify the destinations of light and matter. Anti-de Sitter space gives infinity a surface on which a lower dimensional theory can be defined. Holography suggests that such a surface may contain a complete description of everything inside. The word edge survives, but now names a family of limits revealing different aspects of space, time, causality, and information. Some edges are observer-dependent. The particle horizon surrounds every location because every observer receives signals from only a finite region of the past. Moving to another galaxy shifts the horizon rather than approaching a universal shell. Nothing special must exist at its surface. The boundary arises from the finite age of cosmic communication. Other edges are more global. A black hole event horizon separates paths that can reach distant observers from paths that cannot. Its location depends on the full future of spacetime, yet an infalling object can cross it without encountering a solid barrier. The horizon is physically meaningful because it changes which signals escape, but it is not a material membrane in classical relativity. It is a boundary written into causal structure. A mathematical edge can be equally subtle. The rim of a Poincaré disk represents points infinitely far away in hyperbolic space. It appears close on the page only because the scale shrinks toward the circumference. The rim can organize directions, boundary conditions, and field behavior without becoming reachable. A Penrose diagram performs a related compression for spacetime. Its edges distinguish spatial infinity, light-like infinity, and the remote futures of massive objects. These lines are not walls. They are the finite image of endless paths. Yet calculations performed with them can predict radiation, scattering, horizons, and the fate of information. The map is not the territory, but the map may expose structures that belong to the territory. This creates a philosophical boundary of its own. When does a mathematical construction become part of physical reality? Physics does not answer by demanding that every entity be touched. Many accepted structures are known through their effects and through the consistency of the theories that contain them. Space-time curvature is not held in a hand, yet falling bodies and bending light reveal it. A quantum field is not a visible fluid, yet its excitations appear as particles. The boundary at infinity may be similar, it may not be an object, but it can be part of the framework that determines which events are possible. If changing boundary conditions changes the physical solutions, then the boundary has operational significance even when no traveller reaches it. Anti-de Sitter space strengthens this possibility. There, the boundary at infinity remains in causal conversation with the bulk. Fields require rules at the boundary for their evolution to be complete. Signals can travel outward and return. The lower dimensional boundary can support a quantum theory capable of describing the higher dimensional gravitational interior. The edge is not merely a label attached after the geometry is understood. It participates in the definition of the system. The holographic correspondence goes further by treating bulk and boundary as equivalent. If that equivalence is exact, then the boundary theory is no less real than the interior theory. Each contains the same information. Asking which is fundamental may resemble asking which language owns a story whose complete structure belongs to both. Even so, caution remains essential. The observed universe is not known to possess the anti-de Sitter geometry, where holography is best understood. Cosmic expansion appears to be accelerating, and the large-scale space-time resembles a form with positive rather than negative curvature through time. Its future boundary is not the time-like cylinder of anti-de Sitter space. The clear translations that work there do not yet provide a complete holographic account of the real cosmos. There are suggestive proposals, but no finished theory showing every galaxy and field encoded on a known physical surface. The success of one geometry does not settle another. The possibility remains open, not confirmed. The same caution applies to infinity itself. Observations show that the visible universe is extremely close to spatial flatness, but no finite measurement can prove that space continues forever. A finite universe with an enormous curvature scale could look flat across the observable region. A locally flat universe could possess a connected topology that wraps around beyond detection. Inflation may have expanded the total cosmos far beyond the visible patch, perhaps effectively without limit, but the full extent remains beyond direct observation. Science can constrain accessible space and search for repeated patterns, yet it cannot survey an endless universe to verify that no edge appears. Infinity is therefore a conclusion drawn from models, symmetry, and extrapolation rather than from a completed survey. A physical edge is difficult to define without placing the universe inside something larger. If space ended at a boundary, the phrase beyond the boundary would seem to ask for another location. But location is already part of space. An exterior could not simply be empty space, because that would extend the universe. It would need to be the absence of spatial relations altogether. No direction would lead into it, no distance would measure it, and no clock would record a passage there. Such an edge would not resemble any border in ordinary life. It might be a limit where laws and geometry cease to apply, but then the language of what lies beyond would lose its foundation. The question would fail, not because an answer is hidden, but because the concepts used to ask it no longer operate. Cosmology has met similar limits near classical singularities. The equations predict incomplete paths or divergent curvature, signaling that the theory can no longer describe what happens. A singularity is not necessarily a physical object waiting at the end of a path. It may mark the breakdown of general relativity and the need for quantum gravity. Some edges may therefore be edges of theories rather than edges of nature. The Big Bang boundary in a classical diagram may represent the earliest moment the model can reach, not an absolute beginning of all reality. A future singularity may mark another failure of description. Better theories could replace sharp boundaries with transitions or quantum structures that current concepts cannot express. The apparent edge might retreat when the mathematics deepens, just as the black hole horizon ceased to be a coordinate singularity when better coordinates were used. Yet other boundaries may remain even in a final theory, because causality and information require them. A horizon may be observer-dependent and still shape every possible measurement. A conformal boundary may be unreachable and still encode a complete set of physical states. An edge can be real without being material, and mathematical without being arbitrary. Reality in modern physics often belongs less to objects than to relationships. A horizon is a relationship between events and possible signals. Curvature is a relationship among distances and paths. Entanglement is a relationship among quantum systems. A holographic boundary may be the fullest expression of such relational reality, holding the interior not as a miniature picture but as a web of correlations. The infinite universe may therefore have no edge that can be found by travelling, while possessing edges found by asking where information begins, where it ends, and how the whole can be described. The final answer depends on which meaning of edge is carried into the question. As a physical wall at a finite distance, infinity has none. As an observational limit, every observer has one. As a causal divide, horizons form around black holes and within expanding space. As a mathematical structure, infinity can be compactified into precise boundaries. As a possible foundation for quantum gravity, a boundary may contain the same physics as an entire higher dimensional world. These answers do not collapse into one. They remain layered, each correct within its own domain. The universe does not offer a final shoreline, but it repeatedly creates limits that behave like shores for sight, influence, calculation, and information. Perhaps the deepest mystery is not whether infinity ends, but why the mathematics of an unreachable edge can describe the interior so well. The boundary may be a human tool, a genuine feature of space-time, an alternative form of the universe, or all three at once. At the largest scale, the cosmos remains open not only in extent, but in meaning. Its edge recedes from every journey, yet returns wherever knowledge reaches its limit.